Okay, example 6. Example 6 and 7 are going to take some time. These are a little bit lengthy to do, and hopefully, as you've noticed, if you got the printout here, there is a completely blank next page, and that's because it's basically like doing two problems in one. The reason for that is because if you notice, the very first thing it says here is verify Stokes' theorem. Verify Stokes' theorem. When it says verify Stokes' theorem, what that really is saying is you need to do both methods. We need to do the line integral and we need to do the double integral of the curl ds. So we need to do both of them, and it really doesn't make any difference which one you choose to do first. You need to do both, and this is something that's going to come up again, so make sure that you are at least able to do these problems. Okay, so it says to verify Stokes' theorem, given that the vector field F and the surface S is given to us. The vector field F is there. The surface here is the part of the paraboloid z equals x squared plus y squared that lies below the plane z equals 1 and is oriented upwards. So we are looking at the paraboloid, which opens up. So you're going to have your paraboloid, which opens up, which looks something like that. And then it's got to stop at z equals 1. So it's going to basically look like that bowl right there. And it does say that it is oriented upward. So that means as you're looking down on this thing, it's got to be counterclockwise rotation around C, which goes like that. Alright, so it doesn't really matter which one. I'm going to choose to do the line integral first. You could do the other one first. It doesn't really matter. So let's go ahead and compute our line integral over C of f dot dr. So we need to parameterize our C. And again, C is just the ring around the outside in this case because it's just the line integral. So x in this case is going to equal r cosine theta, but r itself here is 1 because it says that this thing stops at z equals 1. So x squared plus y squared equals 1 means you have a circle radius 1. So x is going to be r cosine theta, or 1 cosine theta. So we're just going to write cosine theta. Y then would be sine theta, and since we're looking from above, we know that that's the correct rotation. And z here is just 1. So that's going to be our r. So now we're going to need to parameterize f. So f parameterized, let's see, y squared is going to be sine squared, and x is going to be cosine, and z squared is just 1. And I'm going to actually go ahead and just make sure I stay proper notationally there. So we're going to call that f of r of well, in this case theta, not t. F of r of theta. Okay, we're also going to need the derivative of r, so we need r prime of theta. And remember, all this stuff up here represented r, so r prime is going to be negative sine theta, cosine theta, and 0. So there is r prime. Okay, we need to dot those two things to take the integral. The integral itself is going to go from 0 to 2 pi, since it's just a circular region. Let's see, dotting these things, we're going to get negative sine times sine squared. I'm actually going to leave it like that. I'm not going to write it as sine cubed because I know that I'm going to have to separate these things in order to reduce this a little bit. So I'm going to write it as negative sine times sine squared theta plus, looks like just plus cosine squared theta plus 0 d theta. Okay, and I'm going to go ahead and separate these integrals because I know that I'm going to have to do two different processes for the first part and the second part. So we're going to have 0 to 2 pi. I'm going to pull the negative out front from the first one, of sine theta sine squared theta d theta plus the integral from 0 to 2 pi of cosine squared theta d theta. Okay, in the first one, I'm going to have to rewrite that sine squared in terms of cosine so that I can do a u substitution. So I'm going to do 1 minus cosine squared for sine theta. So we're going to rewrite this 0 to 2 pi sine theta 1 minus cosine squared theta d theta. And in the second one, we're just going to do a reduction. We're going to change cosine squared to 1/2 1 plus cosine of twice the angle d theta. All right, so let's go ahead and do our u substitution. I'm going to scroll this down just a little bit. Do my u substitution in the first one. So u here is going to be cosine of theta, which means that du is going to be negative sine theta d theta. And so d theta is going to be du over negative sine theta. Now, once again, if you're really paying attention to this, you realize that once I let u be cosine, my integral is going to be 0, because if I change my bounds, plugging 0 in for cosine of theta is going to give me 1. Plugging 2 pi in for the bound is going to give me 1. So the rest of this doesn't matter, because this whole thing right here is going to be 0. Wonderful. Okay, we're done with that part. Let's go back to the other one. This one actually is going to give us a value here. So we're going to have to take the antiderivative. So we're going to have 1/2 out in the front. The antiderivative is going to be theta plus, don't forget the extra 1/2 here, sine of 2 theta. And we'll evaluate that from 0 to 2 pi. So plugging in 2 pi, I'm going to get 1/2 of 2 pi plus 1/2 of sine of 4 theta, but that's 0. And then plugging 0 in for theta is 0 plus another 0. So what I get is 1/2 of 2 pi, or pi. Okay? So now we have to, according to the problem, we have to verify that this is the same. So basically, we know that this should be our answer. Now we have to do it by using the curl method, the curl.ds, and see if that's going to give us pi as well. So let's hope that this works out, and we'll use the second page to do that. So let's move on to the second page here to give us some room. And again, what we're doing now is we're going to use the double integral. And again, I'm going to write this as the double integral over d of the curl of f dot n dA, as opposed to the curl of f dot ds over the surface. Same thing, but this is the way we're going to do this problem. So let's verify now. Let's do the curl. Curl of f I j k d dx d dy d dz. And let's see, let's scroll back up here to see what that was again for f. All the way back up to the top. Y squared x z squared. Okay. So we've got y squared x z squared. So let's compute the curl. Eliminating the I row and column, the partial derivative of y with respect to y of z squared is 0. Partial derivative of z with respect to, of x with respect to z is 0, so that's 0. The j row and column, partial with respect to x of z squared is 0. Partial with respect to z of y squared is 0. That's nice. And then the k row and column, partial with respect to x is 1. Partial with respect to y is 2y, so it's 1 minus 2y. We're going to have to figure out what our cross product is, so we're going to go ahead and parameterize this. Looking at the original functions, I think that the easiest thing to do would be to keep it as a trivial parameterization. Again, you could go ahead and change this to polar right now and do it that way. I'm personally going to keep it as trivial. It doesn't make any difference. So I'm going to let x equal x. I'm going to let y equal y. And then z, if I'm not mistaken from the original problem, without scrolling back up there, z was x squared plus y squared. So that should be a pretty easy one. X squared plus y squared. That's my parameterization, so that's basically r. I just didn't write it in the notation. So we're going to do r sub x, which is going to be 1, 0, 2x. We're going to do r sub y, which is going to be 0, 1, 2y. And then we're going to need the cross. R sub x cross r sub y. So eliminating the I row and column here, we're going to get 0 minus 2x. Eliminating the j row and column, we're going to get 2y minus 0, but we have to change the sign. And then eliminating the k row and column, we just get 1. Okay, and that's good because, once again, the 1 here says that this is upwardly oriented. And you might ask yourself, and I'll actually sketch this for you real quick, well, that's great, but what about this x and the y? Why are those things negative? Well, I'll show you real quick here, just so you have some kind of a geometric understanding of what we're looking at. So again, this was our bowl. So what it's saying is, the z portion is upwardly oriented. That's fine. It's going like this. It's coming out of this this surface or this ring right there in that fashion. In order for it to do that, because we're using the cross product, the x's and y's have to be in a negative or inward direction. Remember that the cross products means that they are parallel to the surface. So in order for this to stay parallel to the surface, it has to be going this way. Right? These vectors right here are parallel to the surface as they move in that direction. And then, of course, they're going to flow upwards as well. So they are moving parallel to the surface, but up, but they're inward, which is why the x and the y components are negative. So hopefully that makes sense. And then, of course, as they hit the ring surface on the top there that's surrounded by your C, they're going to stay parallel to that and go straight up. So that's what the 1 means. So we're good to go there. Okay, so now let's go ahead and go back. The nice thing about this one, again, is when I dot the cross product with the curl, the first two components of the cross product don't matter because the first two components up here were 0. So it's 0 and 0, and then the last one is just 1 times 1 minus 2y. So this really isn't going to be too bad. So we're going to have our double integral of 1 minus 2y dA over d. So let's go ahead and figure out this, excuse me, let's go ahead and figure this thing out. Now, it is a circular region that I am going to do this over top of, so we're going to go ahead and change it into polar now. So we are going to re-parameterize it now. So let's see. R in this case, I'm going to have to go back up to the top. Oh no, z in this case was 1. So since 1 equals x squared plus y squared, that means r is going to go from 0 to 1. So I know that my r is going to go from 0 to 1. We know theta is going to go from 0 to 2 pi. I'm going to reparameterize 1 minus 2y, but y is going to be r sine theta. So it'll be 1 minus 2 r sine theta. And I am reparameterizing it in terms of polar, so I do need the extra r dr d theta. All right, now we should be able to go ahead and just work out the integral here. So let's go ahead and scroll down a little bit, give ourselves some room. And again, we're trying to match, so we're hoping that this whole thing ends up being pi at the end. All right, so we're going to have the integral from 0 to 2 pi, integral from 0 to 1 of r minus 2r squared sine theta dr d theta. And just so you know, if you had parameterized this thing not using trivial, if you had just gone straight into a polar or cylindrical type parameterization, you would have gotten to this step right here, the one I just wrote. That's what you would have gotten. So it might have saved a step or two. It just makes the cross product different. You're just doing it with polar instead. It doesn't make any difference. You choose whatever way is easier for you to do. All right, so let's go ahead and take, now we can't separate this, so we have to do this piece by piece. So antiderivative, first of all, with respect to r, we're going to get 1/2 r squared minus 2/3 r cubed sine of theta, evaluated from 0 to 1, d theta. Plugging in the 1, we're going to get a half minus 2/3 sine of theta. Plugging in 0, we get nothing, so that's good for the first one. And now we'll have to take the antiderivative here with respect to theta. So we're going to get 1/2 theta minus the antiderivative of negative sine there. It's going to be positive cosine. Sorry, I was looking at something else. So plus 2/3 cosine theta. Evaluating that from 0 to 2 pi. Okay, so let's go ahead and plug in the 2 pi. Plug in 2 pi. 2 pi times a half is pi. Plus 2 pi times cosine of 2, 2/3 times cosine of 2 pi, which is 1, is 2/3. Minus. Plugging in 0, you get 0, plus cosine of 0 is 1, so you get plus 2/3. So we get pi plus 2/3 minus 2/3, which again is pi. So it does work. We have verified Stokes' theorem. All right, example 7, last example for this particular section. Consider the surface S described by the paraboloid, which is actually shown there, 16 minus x squared minus y squared, for z is greater than or equal to 0, as shown in the figure. And what they have shown is, on the left-hand side, is the surface of the paraboloid. On the right-hand side is just the c value, the c curve that's actually going to bound this paraboloid. And we want to verify Stokes' theorem for the surface described above. And the vector field that's given is 3y, 4z, and minus 6x. So once again, it doesn't really make any difference which way you choose to do first. You need to do both the line integral and the curl method to verify this. So we're going to go ahead and start off again with the line integral. And the biggest thing is here is, again, what if you were given a problem like this, which way would you do? Would you, if you were only had to try and find the answer, would you do the curl? Would you do the line integral? And that's really where the biggest thing is. It's kind of a trial and error thing until you figure out which way works the best. In this case, obviously, we're verifying, so both of them are going to work out, and they're not going to be terribly difficult. But sometimes some of the math can get really, really messy doing one way as opposed to another. So there is no set thing that tells you which way is easier to do. It's just sometimes it's trial and error. All right, so let's go ahead and do, first of all, let's do the line integral version. So the line integral over c of f dot dr. So we need our parameterized force, and we're going to need our r prime. So first of all, since we're doing the line integral, we are doing this portion right here. I'm going to do this portion right here where I'm tracing the line. I really don't know why I'm trying to do that. I'm not doing a very good job, although it's not horrible. And then, of course, you can see with the arrow, it already is pointing that it's traversing it this direction. So since we are doing the line integral version, we are only concerned with the outside ring. We are not concerned with what's inside of the ring as far as parameterization. So our curve is going to be defined as, let's see, that thing has a a radius of 4. That's because if z is 0, we go up right here, and we would see the x squared plus y squared equals 16. So we would get that x is going to equal 4 cosine theta, and we're viewing it from above, so we know the direction is going to be correct if we just do our standard y equals 4 sine theta. And since this thing is sitting on the xy plane, z is 0. So that's basically your r. So we know we're going to need r prime of theta. So r prime of theta is going to be, let's see, what's that? Negative 4 sine, try and draw an S the correct way. Negative 4 sine theta, 4 cosine theta, 0. Okay, that's r prime. I know I need to do f of r of theta. So my force evaluated at r of theta. Now be careful here, because the first one is 3y, so it's really going to be 3 times 4 sine theta. So that's 12 sine theta. The second component is 4z, but z is 0, so that's 0. And then the third component is negative 6x, and x is 4 cosine, so that's going to be negative 24 cosine theta. All right, and we're going to need to dot those two things. So let's go ahead and scroll down so we can finish up the work here. So we're going to have, we know it goes 0 to 2 pi. We're going to have an integral from 0 to 2 pi. Let's dot f and r prime. So let's see, negative 4 times 12 is negative 48 sine squared. The middle component is 0. The last component is 0, so that's actually really nice. This one actually looks like it's going to work out very nicely for us. So we are going to have to reduce the sine squared. So I'm going to pull that negative 48 out to the front. Reducing sine squared is 1/2 1 minus cosine of twice the angle, which is 2 theta, d theta. Pull that 1/2 out to the front, we're going to get a negative 24. Taking the antiderivative, we now get theta minus, don't forget the 1/2 sine of 2 theta from 0 to 2 pi. So plugging in 2 pi, let's see, we're going to get a negative 24 out front. We get 2 pi. We've done this one several times, or this kind of thing. Just make sure you keep checking, because sometimes things change. You plug 2 pi in for, into the sine, and you're going to get sine of 4 pi, which is 0. Plugging 0 into all the thetas also gives you 0. So we get negative 24 times 2 pi, which is negative 48 pi. Okay, now we have to double check this, or not double check it, but we have to verify that the double integral over s of the curl dot ds is going to be the same thing. So let's go ahead and move on to the next page. So again, we need to do the double integral over s of the curl of f dot ds, which again, I prefer to write it as the double integral over d of the curl of f dot n dA. Okay, so let's go ahead and figure out our curl. The curl of f. Again, I can always write the first two lines because those don't change. And then I got to scroll back up to remind myself what f was. It was 3y, 4z, negative 6x. 3y, 4z, negative 6x. Okay, so let's figure out the curl. So the curl here is going to be, eliminating the I row and column, we're going to get the derivative of, with respect to y, of negative 6x is 0, minus the derivative with respect to z of 4z is 4, so it's just going to be negative, is it negative 4? Yeah, negative 4. Eliminating the j row and column, we're going to get negative 6 minus 0, but you got to change the sign on that, so it should be positive 6. And then eliminating the k row and column, we are going to get 0 minus 3, so that's minus 3. It's kind of nice that the curl are all just numeric values, so when we dot those, it's going to make it a lot easier, I think. Okay, so our surface, which was given to us as z equals 16 minus x squared minus y squared. Again, I'm going to go ahead and do this in trivial right now, and then after I do the whole dot product, I'm going to change it probably into polar because it looks like it'll be easier to do in polar. That's just my choice. You can do it however you want to. So I'm going to do my surface defined as x equals x, y equals y, and z equals, it was 16 minus x squared minus y squared. I don't know. Maybe it's just because I think that the partials are easier to do in this case. I don't know. Rx is going to equal 1, 0, negative 2x. Ry is going to equal 0, 1, negative 2y. And then we have to cross those. So Rx cross Ry Remember, we are looking for a positive or upward orientation, so let's make sure that the z component at the end is in the correct place. Eliminating the I row and column, we get 0 minus 2x, so that's 2x. And then the j row and column, we get negative 2y minus 0, but we have to change the sign, so that's 2y. And then the important one here is the k, so if you eliminate the k row and column, we get 1 minus 0, so that's 1. So that's good. In this case, they're all positively oriented. I'll go back right at the end of the video and just show you why that actually makes sense, looking at the drawing. So now we have the curl, we have our cross product. We need to dot those two things, and then we're going to take our double integral. So we're going to have our double integral. Let's go ahead and dot curl of f and our cross product. So if we dot those, negative 4 times 2x is negative 8x. 6 times 2y is going to be 12y. And then negative 3 times 1 is negative 3. So there's our double integral. We're going to write this over dA. Let's scroll this up so we can finish this off. Okay, so I am going to reparameterize these things now in terms of polar. So it was 16 minus x squared minus y squared. So I know r will go from 0 to 4. And I know that theta, of course, is going to go from 0 to 2 pi. Putting x and y in terms of r and theta, we know that x is r cosine theta, negative 8 r cosine theta. And you might ask yourself, well, again, why am I using r there? Why am I not using 4? Remember, now this is a surface integral. It's the entire surface. It's not just the line integral. So r in this case varies from 0 to 4. Okay, very important. Make sure you're paying attention to that. And then plus 12, and y is r sine theta. And then minus 3. And then this will be dr d theta, but I did reparameterize it in terms of polar, so I do need the extra r. Don't lose that extra r if you do it this way and reparameterize it. If you went ahead and parameterized your surface in polar in the first place, then you wouldn't have to worry about the extra r. Again, I say that a lot, but I'm going to try and keep making sure that you're understanding when you actually do that. Okay, unfortunately cannot separate these things, so let's go ahead and distribute the r. So we're going to get negative 8 r squared cosine theta plus 12 r squared sine theta minus 3r dr d theta. So again, we're going to have to go step by step here. So let's go ahead and take the antiderivative with respect to r. So 0 to 2 pi for my first integral. So we're going to get negative 8 thirds r cubed cosine theta plus 12 thirds, which is the same as 4 r cubed sine theta, minus 3 halves r squared. And we'll evaluate that from 0 to 4 d theta. Going to get some kind of big numbers here. So if I plug 4 in, 4 cubed is 64. 64 times 8, let's see, 64 times 2 is 128, times 2 is 256, times 2 more is 512. Did I do that right? 512, I think. 512 over 3. That is not divisible by 3, so that's it there. 4 cubed again is 64. 64 times 4 is 256 sine theta. And then 4 squared is 16 times 3 is going to be, what is that, 48. So minus 48 over 2, which is 24, I believe. Looks right. Double check that and we'll know at the end if this doesn't work out, because we know what our answer is supposed to be. It's supposed to be negative 48 pi, assuming we did the first one right. All right, so let's take the antiderivative. So if we take the antiderivative of the first one, we're going to get, let's see, antiderivative of negative cosine is going to be negative sine, so it's negative 512 thirds sine theta Antiderivative of sine is going to be negative cosine, so minus 256 cosine theta, and then minus 24 theta. Now, if we were really smart about this, we would have separated all of these integrals, because when you take the antiderivative of cosine, or when you take the antiderivative of just sine, and you evaluate those from 0 to 2 pi, because you're going to end up and start in exactly the same position, they're always going to be 0. So do I really have to plug the 2 pi and the 0 into these first two? Not really. You can, but you don't have to. But this one's going to go to 0. This one's going to go to 0. So really all I have to do is plug 2 pi and 0 into the last one. If you don't believe me, go ahead and plug them in. You'll see that they work out and the values will cancel out for each one of those. But really it's just plugging the 2 pi into the last component. So we're going to get negative 24 times 2 pi minus 0, which is negative 48 pi. So it does end up working out. That's awesome. So now let me go back and show you real quick, and then we'll be finished with this unit, with this particular section here. Remember I said that these two things right here were positive, and of course the z value is positive, which we needed it to be. So let's look at the sketch of the surface, because this one involves the surface. So if we go back up here to the surface, it makes sense that the x's and the y's were positive as well as the z. I mean, it tells you the z right up on the top here. You can actually see that right there. They've given that to you. The z is up, which is good. It's positive. But the x's and y's being positive makes sense because, again, staying parallel to the surface, they've got to come out of the surface in that direction. Those are upward and positive, and in positive x and y directions. So it does actually make sense that the x and the y components of the cross product were positive. All right, so there you go. We have verified, we have found Stokes, used Stokes' theorem to evaluate these things. Given one, you usually use the other one if it tells you to use Stokes' theorem. The problems are not short. Take your time, be careful on them, but they are doable.